This video is sponsored by KiwiCo. More on them later. This is Kepler's impossible equation. Kepler famously discovered that the planets sweep out equal areas and equal times on elliptical orbits. But to actually use this fact, we have to compute the angle theta that the planet makes to the body it's orbiting. Inscribing Kepler's ellipse into a circle, we can show that the area swept out by the planet, plus this extra triangle, is proportional to the area that would have been swept out on a circular orbit. With some algebraic manipulation, we arrive at a pair of equations, one that connects time to the central angle E, and one that connects E to theta. Now, to do much useful astronomy, we need to be able to solve for E in the first equation, so we can predict where the planet will be at some future time t. Kepler wasn't able to solve this equation when he discovered it in 1605, and we've literally been trying ever since. Here's an attempt from 2024. Why is such a simple-looking equation so difficult to solve? How do astronomers actually use Kepler's laws without being able to solve for the angle E? Over the next 250 years, the search for a solution to Kepler's equation would be a key part of the expansion of the frontiers of mathematics, not once but twice, and ultimately lead to an elegant theory of convergence for infinite series that today is a cornerstone of modern analysis. These are the Rudolphine tables. Published by Kepler in 1627, they predict the position of the planets about 30 times more accurately than previous approaches. How did Kepler get around his unsolvable equation to make these predictions? An interesting property of equations like Kepler's is that while there's no obvious way to solve for E, it's very easy to check if a given E value is any good. All we have to do is plug some estimate of E, let's call it E hat, into Kepler's equation, and see how close the resulting value is to the value of m that we're looking for. Kepler used this fact to create a simple guessing and checking algorithm. To estimate where the planet Mercury will be on a given date, let's say December 25th, 2024, we first compute the time elapsed since Mercury was at its last perihelion. This is its closest point to the Sun, and the one closest to December 25th happens on December 6th, 2024, giving a difference of 19 days. From here, we can compute the m in Kepler's equation. This is the angle the planet would have swept out if its motion was uniform around the Sun. Mercury will cover a full 360 degrees or 2 pi radians in 88 Earth days. So the angle m is equal to our lapse time of 19 days divided by 88 times 2 pi, giving an m value of 1.36 radians or 77.7 degrees. Of course, as Kepler showed, the planets do not actually follow uniform circular motion, and Kepler's equation tells us how the actual central angle E varies with m, when the planet's motion follows Kepler's equal area law while traveling on an ellipse with eccentricity of little e. The eccentricity just measures how squished the ellipse is. An ellipse with an eccentricity of 0 is a circle, and once eccentricity reaches 1, the ellipse breaks and turns into a parabola. Kepler had a good estimate for the eccentricity of Mercury's orbit, so from here he just needed to find an angle E that would return a value close enough to m when he plugged it into his equation. He started with an initial guess for E. One simple approach is just to set E hat equal to m. From here we can plug E hat into Kepler's equation and compute m equals 66.0 degrees, which is a bit smaller than the true value of m. To get closer to the true value of m, we need to increase the value of E hat. But by how much should we increase it? Kepler found a simple approach that works remarkably well. Compute the error between m and our estimate of m hat, and add this error to E hat to get a new value of E hat. So we're increasing our guess for E by exactly the error between the true and estimated value for m. After just 2 iterations of this process, our error shrinks to just 0.0004 degrees, well within the measurement error of the observations Kepler was using. Kepler doesn't give an explanation for how he landed on this exact approach. Why does adjusting our guess by exactly our error at each step work so well? Interestingly, if we modify Kepler's method to adjust our guess for E by twice the error at each step, it doesn't work at all. And if we only adjust by half the error at each step, it converges much more slowly. To see why Kepler's approach works so well, it's helpful to plot the value of m across a range of E values. In the case of a purely circular orbit, our eccentricity little e is just 0, and m just equals E, so our plot is just a straight line with a slope of 1. As eccentricity increases and our orbit becomes less circular, we're effectively subtracting a scaled sine wave from our straight line, causing it to bend downward between 0 and 180 degrees, and bend upward between 180 and 360 degrees. Higher eccentricities make the relationship between time and the planet's position less linear, with the planet moving more quickly close to the Sun and more slowly when it's further away from the Sun. Solving Kepler's equation for m equals 77.7 degrees is equivalent visually to figuring out where our curve intersects the horizontal line at m equals 77.7. Our initial guess for E, 77.7 degrees, shows up here on our plot. And following Kepler's approach, we plug this E hat into Kepler's equation, effectively computing this point on our curve. We then computed the error by subtracting our estimate of m from the true value of m. This is just the distance between the point on our curve and the line. From here, Kepler's approach tells us to add this error value to E hat, effectively moving us to the right on our plot by this error value, and making nice progress towards our true solution, where our line and curve intersect. Subsequent steps get us closer and closer to the true intersection value. Now, the reason this works so well for Kepler's equation is because the EM curve is reasonably close to a straight line with a slope of 1. If our eccentricity was 0, making our orbit circular, Kepler's approach would work perfectly in just one step. Since our curve in this case is just a straight line with a slope of 1, adjusting E by the error term gets us exactly to the right solution, since the base and height of our triangle are equal. So Kepler's method works well when eccentricity is low, and the EM curve is close to a straight line. Of the 6 known planets when Kepler published the Rudolphine tables, Mercury has the highest eccentricity at 0.21. The worst case position on this orbit, where m is around 140 degrees, requires 4 steps of Kepler's method to achieve sufficient accuracy, which is not ideal when you're performing computation after computation to create something as extensive as the Rudolphine tables, but still is a viable approach. 6 decades later, around 1670, Isaac Newton would pick up where Kepler left off, making a significant improvement to Kepler's method, now known as the Newton-Raphson method, and used on a huge variety of problems. Newton used a geometric construction to estimate the slope of the curve at E hat, and used this information to make smarter updates to E. Using Newton's method, we're able to estimate E in the Mercury case with sufficient accuracy in just 2 steps. A decade later in 1680, an incredibly bright object appeared in the sky that would challenge both Kepler and Newton's numerical approaches. The Great Comet of 1680, reportedly bright enough to see in the daytime, and with an incredibly long tail, was seen by many as an omen of the end of times. Here's a sermon about it from the Reverend Increase Mather, given on January 20th, 1680 in Boston. Back in England, Newton's colleague Edmund Halley began to hypothesize that comets actually orbited the Sun as the planets did, and that their arrivals could be predicted. Comparing observations of the motions of various historical comets, he conjectured that the comets seen in 1681 and 1682 were actually the same comet Kepler had seen 75 years earlier in 1607, as he worked to publish his laws. But for the math to work out, the comet's orbit would have to have an incredibly high eccentricity. We can explore how Kepler and Newton's numerical methods handle these higher eccentricities by constructing a 2D grid of test cases, where the y direction captures the eccentricity of the orbit, and the x direction captures the position of the object on its orbit. Running Kepler's method in each grid cell for 6 iterations, we can visualize the final error using a heat map. At an eccentricity of 0.97, this is approximately the eccentricity of the orbit of Halley's Comet, Kepler's method gives a massive worst-case error of 20.6 degrees. Newton's method fares better, but still yields significant error when the comet is close to the Sun. Visualizing our iterations on our EM curves, we can see that the high slope caused by the comet's highly eccentric orbit causes Kepler's method to jump around the correct solution, and the high curvature causes Newton's method to overshoot the correct answer, requiring more iterations. From here, there's a range of numerical approaches we can take to address these issues. Halley would successfully use a different formulation of the problem that was more tractable for high eccentricities. However, at the end of the day, all of these methods are just refinements of Kepler's guess and check idea, and can be imprecise, messy, require significant computation, and it can be difficult to know when a given technique will work well. With the digital computer still 3 centuries away, astronomy would benefit greatly from a more direct solution to Kepler's equation. After all, why can't we just solve for E? The next century would bring the development of new sophisticated mathematical tools that would allow E to be expressed as the sum of various infinite series, and would ultimately lead to an elegant theory of convergence for these series that today is a cornerstone of modern analysis. While they didn't push the frontiers of mathematics forward, there were also a number of physical devices designed and built to solve Kepler's equation. There's a set of purely geometric solutions that give approximate answers to Kepler's equation. In the early 1900s, Arthur Rambaud turned this construction into a physical device, where the value of m could be set on a dial, and an approximation of E could be found by taking readings of where this string intersects the dial. There's nothing quite like building something physical like this for developing understanding, which is why I was more than happy to partner again with this video's sponsor, KiwiCo. Now is a great time to have a fresh look at KiwiCo, as they've just announced a big change to their lineup. Kids now join one of 5 clubs, where each crate is part of a learning series, meticulously designed to build up specific skills and knowledge over the long run. This is such an important part of learning and mastery. Growing up, I was obsessed with electronics, and was lucky enough to be able to progress from taking apart old electronics to building a computer from parts with my dad to soldering my own audio amplifiers like this one. It sounded terrible, but was a ton of fun and such a cool learning experience to progress from taking things apart to reading books to making my own circuits. Skills and experiences like these can really compound until you've arrived somewhere you could have never imagined. With clubs, KiwiCo is boxing up these long-term learning arcs. I'm really excited to see my kids progress through the Panda and Sprout clubs. When my daughter turns 6 in a few years, she can join the KiwiCo Labs Club. Aside from being a great name, KiwiCo Labs helps kids progress from science to engineering, and includes brand new rebuildable STEM projects like games and robots. Sign up for a KiwiCo club today using code WelchLabs to receive 50% off your first club crate when you join a club for kids age 3 and older, or visit kiwico.com/WelchLabs. Huge thanks to KiwiCo for sponsoring this video. Now back to Kepler's impossible equation. In the 18th century, mathematicians began to tame infinity. Like imaginary numbers, infinitely large and small numbers open up new ways of attacking problems. For example, we can use a Taylor expansion to break apart the sine term in Kepler's equation into an infinite sum of simple polynomial terms. Each term contains higher and higher order derivatives of the sine function, which tell us how much of each polynomial to add together to recreate the sine curve. In the late 1700s, Joseph Louis Lagrange, while trying to solve Kepler's equation and other similar problems, remarkably found a way to create Taylor series for inverse functions. Let's temporarily switch Kepler's equation to a more familiar f of x notation, and see how Lagrange's result applies. So we now have y equals f of x defined as x minus e times the sine of x. Solving Kepler's equation with these new symbols means solving for x, or equivalently finding the inverse function of f. The Lagrange inversion theorem says that we can express x or f inverse as a fairly complicated looking infinite sum. The thing to note here is that the sum does not involve f inverse itself, which of course we don't know. It instead involves the derivatives of f, which we do know. Applying Lagrange's inverse theorem to Kepler's equation, we're able to make some simplifications and arrive at this infinite sum, where the coefficient of each term is equal to a derivative of sine to the power of our term's index n times e to the power of n. This formula has a similar shape to the Taylor expansion we saw earlier for sine of x. But interestingly, our powers are of the eccentricity of the ellipse e, not x or y. Switching back to e and m for x and y, we now have a fully solved expression for e. So did Lagrange solve Kepler's equation? Let's try out Lagrange's solution and see. Let's take the example of computing the position of Mercury that we considered earlier. We'll use 0.21 for the eccentricity little e, and let's say again that we're trying to find the position of Mercury on December 25th, 2024, which leads to an m value of 77.7 degrees. From here, all we should have to do is plug in little e and m, and see what Lagrange's solution returns. Now, Lagrange's solution includes an infinite sum, and of course we can't compute every term. Let's start with the first few terms and see how we do. The first term evaluates to the sine of m times e. Computing our second term requires us to take the derivative of sine squared, resulting in the sine of m times the cosine of m times e squared. The calculus really starts to pile up on the third term, requiring us to compute the second derivative of sine cubed of m. Stopping at 3 terms for now, we can plug in our m and e values for Mercury and directly compute e equals 89.8 degrees. We can measure the error in the same way we did with Kepler and Newton's method, by plugging our estimate of e back into Kepler's equation and computing the error in terms of m, giving an impressive error of only 0.02 degrees. So how does Lagrange's infinite series compare to Kepler and Newton's numerical methods? Plotting our errors across a full orbit of m values for Mercury, we see that Lagrange's method outperforms Kepler's approach, but not Newton's. Newton's method converges remarkably quickly to very low errors for low eccentricity orbits like this. But what about high eccentricity orbits, where we saw Newton and Kepler's methods struggle? Moving to the higher eccentricity value for Halley's Comet of 0.97, we see that Newton's method still generally outperforms the Lagrange inversion, except for the M region around 6 degrees, where the comet is close to the Sun. Of course, we're only using 3 terms from Lagrange's infinite series. Let's compute 3 more terms and see how this impacts our results. As we can see, moving to 6 terms, the performance of our Lagrange inversion actually gets worse. Why would more terms of our series make our estimate of E worse? Is the Lagrange inversion theory even correct? Returning to the lower eccentricity orbit of Mercury for a moment, we see that performance improves as we move from 3 to 4 to 5 to 6 terms of the Lagrange series, as expected. Why would Lagrange's series work for one ellipse but not for another? For what values of our eccentricity E does adding more terms of our Lagrange series start to make things worse? In 1798, Pierre-Simon Laplace began publishing his massive and highly influential 5-volume treatise on astronomy, Mécanique Céleste, where he immortalized Lagrange's solution to Kepler's equation. Laplace was aware that the Lagrange inversion didn't always work, computing that the series would diverge for eccentricity values larger than 0.66196. But Laplace did not rigorously justify this claim. The early 1800s brought a formalization and unification of calculus, led by the mathematician Augustin-Louis Cauchy. Studying Lagrange's solution to Kepler's equation led Cauchy to an elegant and precise method for determining when a series like the Lagrange inversion would converge. Reportedly, when Cauchy read his paper on convergence of series at the French Academy of Sciences in 1831, Laplace was in the audience, and ran home immediately after the meeting to see if he had published any divergent series in Mécanique Céleste. So how does Cauchy's method work? Let's consider the power series for the function 1 over 1 plus x squared. Using a Taylor series, we can expand this function as 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, and so on. Plotting the function and its Taylor expansion as we add more and more terms, we can see that the expansion starts to break down around x equals plus or minus 1. For x values between minus 1 and 1, additional terms make our Taylor series more accurate, while outside of this region, more terms actually make the expansion worse, just as we saw for the Lagrange inversion applied to Halley's Comet. But what's special here about plus and minus 1? Why does the expansion stop working at these values? Cauchy showed that there is a simple and general answer, but to see it we have to expand x to be a complex number with real and imaginary components. We can visualize the value of our function when x is a complex number as the height of a surface above the complex plane. Our original curve is directly above the real axis, and now fits into a broader surface. Note these big singularity spikes we see at x equals plus or minus I. Our function is not defined here, since I squared is minus 1, resulting in 0 in our denominator. Remarkably, it turns out that the location of these spikes has everything to do with why the Taylor series of our real function diverges at plus or minus 1. In this example, our Taylor expansion is taken around the origin, and the distance between the origin on our complex plane and these singularity spikes is 1. What Cauchy rigorously proved is that the radius of convergence is equal to the distance from the center of our expansion to the nearest singularity on the complex plane. This importantly works for points other than the origin. If we had taken the Taylor expansion of our function around x equals 1/2, for example, our Taylor expansion looks a bit different, and continues to match our function beyond x equals 1. But where exactly does it diverge? What Cauchy is telling us here is that the radius of convergence is exactly the distance between x equals 1/2 and our nearest singularity on the complex plane. In this case, x equals I. This distance comes out to the square root of 1 squared plus 1/2 squared, so the square root of 5 over 4, about 1.118. In general, we can write the radius of convergence of our function as r equals the square root of 1 plus k squared, where k is the center of our expansion. Cauchy applied a similar, but necessarily more complex approach to the power series for the Lagrange inversion, and showed that the series would converge for e values less than the square root of r squared minus 1, where r is defined as a fairly complicated function of exponentials. Solving for r and then for e, Cauchy showed that the series will converge for e values less than 0.6627434. This constant is known today as the Laplace limit. So the Lagrange inversion will only converge for orbits with eccentricities below this value. At this point, it's fair to wonder what astronomers are really getting from all this mathematics. After all, Newton's and even Kepler's method work well for lower eccentricity orbits, and are simpler to use. By 1860, work on Kepler's equation was mostly bifurcated into astronomers using numerical or hybrid methods to get answers of sufficient accuracy as quickly as possible, and mathematicians using transcendental equations like Kepler's to push the boundaries of mathematics. As happens so often with mathematically driven pursuits, the search for a solution to Kepler's equation led to the creation of entirely new mathematical tools that have broad application outside of the initial problem statement. In the decades after Lagrange applied his inverse methods to Kepler's equation, the mathematician Friedrich Wilhelm Bessel took a fresh look at the problem and developed what we now call Bessel functions. Like Lagrange's solution, Bessel functions allow us to solve Kepler's equation using an infinite series, but using sine functions instead of powers of e. Like the Lagrange series, the Bessel series was more complex to work with and less accurate than competing numerical methods. But Bessel functions themselves have turned out to have an absurdly broad range of applications, from acoustics to electromagnetism, such as predicting the diffraction behavior of light through helical objects like DNA. Today, Cauchy's radiance of convergence, and more broadly the powerful idea of working with functions in the complex plane, are key parts of modern analysis. It's incredible to see how far the search for solutions to Kepler's simple equation has taken us in the 4 centuries since Kepler encountered it, and there remains new angles to be explored. Here's 17 different papers on solutions to Kepler's equation, published in just the last 5 years, including new numerical and analytical approaches. We'll have to wait and see where the hunt for the solution to Kepler's impossible equation takes us next. If you enjoy Welch Lab's videos, I really think you'll like my book on imaginary numbers. It's coming out later this year. Way back in 2016, I made a massive 13-part YouTube series on imaginary numbers. It's such an incredible topic. I released an early version of this book back then, and I'm now in the process of revising, correcting, and significantly expanding it. My goal is to create the best book out there on imaginary numbers. High-quality hardcover printed books will start shipping later this year. You can pre-order a copy today at the link in the description below. And your order includes a free PDF copy of the 2016 version that you can download today. You'll find all of this and more at the Welch Labs store.